Sorry, the last video, I ran out of time. This is my cat, Polly. She wandered in here, so I thought I'd show you. She's not very nice, but I still love her. So, she's gonna run away now. Anyhow, so what we just did was we found the moles of potassium ions in the sample. All of the, oh no, wrong way. There we go. So we found the moles of potassium ions in the sample. Now we're going to look at the ratio of potassium ions per unit, formula unit, of potassium permanganate. So since that's a 1-to-1 ratio, there's 1 mole of potassium ions in 1 mole of potassium permanganate. We know that we have 0.492 moles of potassium permanganate. Now we can find the grams of potassium permanganate that 0.492 moles would be. So we're going to convert that 0.492 moles into grams by multiplying by molar mass. That should say grams up here, missing my unit. And then we find that there are 77.77 grams that were in the assumed 100-gram sample. So that tells us that the percent of potassium permanganate in the sample is going to be 77.77% or 77.8%, however you want to round it. Now there is another way to do it, and this might be easier for some of you. I typically do that way because when we get to combustion analysis, typically that's the way that you kind of go about it, maybe not. But the ratio of the molar mass of potassium permanganate to the molar mass of potassium ions is going to be equal to the ratio of the mass percent of potassium permanganate to the mass percent of the potassium ion. So what that would look like is basically the molar mass of potassium permanganate, which is 39.1 grams plus 54.94 grams plus, and then 4 times 16 because we have 4 oxygen. My writing is not very good when I'm using my mouse. And that's in grams or AMU, divided by, we have 1 potassium atom times the molar mass or AMU for 1 potassium ion, which is 39.10 grams. Okay, so that's the ratio of the molar mass of potassium permanganate to the molar mass of a potassium ion. Then we set that equal to the percent of potassium permanganate, which is what we're trying to find, over the percent of potassium ion, which they give us in the sample, 19.24%. Okay, so that has to do with the law of definite proportions and the fact that the ratio of ions per formula unit is going to be the same as the ratio of the percent for the percent of the formula as well. So now, since we're solving for this here, we can cross multiply and solve for the percent KMnO4. So that's this times this divided by this, and you should get the same answer, 77.77%. Okay, so that's another way to do it. The other way just like conceptually makes sense to me, which is why I use it. But if this makes more sense to you, then you're free to do it that way. So there is more than one way to solve this type of problem. Okay? Next, we're going to talk about molecular and empirical formulas. The molecular formula is the chemical formula that provides the actual number of each type of atom in a molecule. The empirical formula is a chemical formula that tells us the relative number of each type of atom in a molecule, which is basically the ratio in simplest forms. So molecular formula tells us the exact composition. The empirical formula kind of tells us the ratio of elements in that compound. So empirical formulas are written as the smallest whole number ratio from one atom to another, and molecular formulas are written using the actual number of each atom contained within a molecule. So here, hydrogen peroxide, the actual number of hydrogen atoms and oxygen atoms in one molecule of hydrogen peroxide is 2 of each, H2O2. The empirical formula, the ratio of hydrogen to oxygen atoms, is 1 to 1. Because you can look at this, you could reduce this from 2 to 2, both are divisible by 2, to go 1 to 1. So it's HO as the empirical formula. Ethylene, C2H4, has exactly 2 carbon atoms and 4 hydrogen atoms in one molecule. The ratio of carbon to hydrogen is 1 to 2, so the empirical formula is CH2. Dextrose, which is a type of sugar, is C6H12O6 as its molecular formula. So there are 6 carbon, 12 hydrogen, and 6 oxygen in one molecule of dextrose. The ratio of carbon to hydrogen to oxygen is 1 to 2 to 1. So the empirical formula is CH2O. The thing about empirical formulas is that different compounds can have the same empirical formula. So keep that in mind. The empirical formula isn't unique to one molecule. The molecular formula is what's going to make that one molecule unique to another. So here, if we have the molecular formula of water, H2O, to find the empirical formula, we're going to find the lowest whole number ratio of hydrogen to oxygen. In this case, it is still 2 to 1, so the empirical formula is the same as the molecular formula, which is fine. Acetylene, C2H2, lowest whole number ratio, you should find to be 1 to 1, so it's CH for the empirical formula. And hydrazine, N2H4, lowest whole number ratio should be 1 to 2, so the empirical formula is NH2. Other compounds can have the same empirical formula. They will not have the same molecular formula. To find the empirical formula given experimental data, this is the little rhyme that we use. It's percent to mass, mass to mole, divide by small, times to whole. Okay, so this describes each step that you go through in the mathematical process to find the empirical formula. Percent to mass, mass to mole, divide by small, times to whole. So here we have a sample of potassium permanganate, sample of caffeine, hang on, let me erase this part. My bad. Just ignore that first part. There we go. That was a typo on my part. We're good. Okay, so we have a sample of caffeine found to contain 49.5% carbon, 28.9% nitrogen, and 16.5% oxygen, and 5.1% hydrogen by mass. We want to find the empirical formula for caffeine. Okay? So, first thing that we have to do is go from percent to mass. So in step 1, we're going to assume 100 grams of a sample, because that's the easiest way. So we would have 49.5 grams of carbon, 28.9 grams of nitrogen, and 16.5 grams of oxygen. Oh, and 5.1 grams hydrogen. Step 2, we're going to go mass to moles. So those masses that we just found, assuming 100%, we're going to convert to moles. We do that by dividing by molar mass. So carbon is going to be 49.5 grams times 1 mole divided by 12.01 grams, and we find that we have 4.12 moles of carbon. Go ahead, pause the video, find the moles of nitrogen, oxygen, and hydrogen. Once you do that, you should find that we have 2.06 moles of nitrogen, 1.03 moles of oxygen, and 5 moles of hydrogen. The next step says divide by small. So those numbers that we just found, we're going to find the smallest number of moles. In this case, it is oxygen. I think I boxed it. So we're going to divide every number that we found by 1.03. We should get 4 for carbon, 2 for nitrogen, 1 for oxygen, and 4.9, which is close enough to 5, for hydrogen. These are all whole numbers, so we do not need to times to whole. That part has been taken care of because these are all whole numbers. So then we just apply those numbers to the elements that they correspond to get the empirical formula C4H5N2O. Okay? To find the molecular formula, we're going to find the molar mass of the compound, which is typically given in the problem, divided by the empirical formula mass, which we can find empirical formula from data given, and that will become our multiplier for the empirical formula to make the molecular formula. So let's go through an example of that. The molar mass of caffeine is 194.2 grams per mole. We need to find the molecular formula for caffeine. So we just found the empirical formula to be C4H5N2O. Now we're going to find the molar mass of C4H5N2O. And that is this math here, which is 97.11 grams per mole. Now basically we're finding how many of these units fit into the actual molecule of caffeine. So this is the smallest whole number ratio. We want to know how many of those ratios go into the actual compound. So we're going to divide 194.2 by 97.11. You should get an answer very close to 2. So this is the whole number that we are then going to multiply each subscript by in the empirical formula to find our molecular formula. So the molecular formula will be C8H10N4O2. Okay? Combustion analysis is one experimental way that we typically get this data for empirical molecular formula problems, and it's pretty simple, which is why it's really common to use that kind of example. But the products for any combustion reaction for a compound containing hydrogen and carbon, or hydrogen, carbon, and oxygen, are always going to be CO2 and H2O. So remember, for combustion to happen, you need O2 added. So you always get CO2 and H2O. If your original compound also had oxygen, you're not really sure if the oxygen came from the O2 or this compound, so we'll kind of go through how to find that. But you can find the percent composition and empirical formula of an organic compound made of carbon, hydrogen, and oxygen by doing this combustion analysis. All of the hydrogen bonds to oxygen to form water, which is then absorbed by the water absorber. And all the carbon bonds with oxygen to form CO2, which is then absorbed by the CO2 absorber. The increase in mass of the water absorber and carbon dioxide absorber can be found, which will allow you to determine how much water and carbon dioxide you have gained. Oxygen is the only one that is added to the system during the combustion reaction, because combustion always takes place in the presence of oxygen. So we always find the amount of oxygen last because there's oxygen in water and in carbon dioxide. So these are the steps that you will take to tackle a combustion analysis problem. You'll use dimensional analysis to find the grams of carbon and hydrogen produced. Subtract the sum of the masses of carbon and hydrogen from the total mass that you started with to find the mass of oxygen. Then you can find the moles of C, H, and O by using the molar mass and going from grams to moles. And then you can find the empirical formula. All right, I don't have enough time to go through this in this video, so I will do another video for this example, so stay tuned.